So we are going to see how to use the implicit differentiation to find the tangent lines at the graph of this equation at these points. So the first thing to do would be, so first let us make sure that these points do lie on this on the graph of this equation. So we would go ahead and substitute and check whether they do. So here we have 1 square, and I think for the sake of clarity it would be good to put multiplication sign here. So we got 1 square, and you might have seen it already that it is 1 plus 1 equals 2. I mean, this quantity is 1, this quantity is 1, and 1 plus 1 is 2. So therefore 1, 1 is a point on the graph. Alright. Now next let's check for -1, 2. So here we got -1 is square, then times 2 is square, and then we got -1 cubed, okay, times 2, and what is that going to give us? Notice this quantity is going to become 4, because -1 square is 1, and this is -1, so that's -2. So 4 minus 2 is 2. So this point is also on the graph of this equation. Okay, now let's check for 1, -2. Okay, so here I'm substituting 1 and -2 in place of x and y. Alright, so here we can remove these brackets. Okay, so we got 1 and -2. So we have 1 cube, and then here we got -2 here. Okay, so sorry about that. So what you have here again is, this is +4, this is -2, and 4 minus 2 is 2. So again what we have is that we got that this point also lies on the graph of this equation. Okay, now we should go ahead and look at graph of this equation by using our GeoGebra graphing calculator. So here we have x square, right, and then we got times y square, right, plus then we have x cubed, okay, and times simply y equals 2. And if we look at a graph, so here GeoGebra, it produces a graph for us, and then we can see in this graph that 1, 1, -1, 2, and 1, -2, they are all points on the graph of the equation that we are looking at. And we can also see in this GeoGebra graph that unique tangent lines are available at the points that we are considering. Now let us go ahead and implicitly find the derivative of y with respect to x. So first let's differentiate I mean, this is not the only way of doing that, but I'm doing it for simplicity, that I'm differentiating this product. So we will go by the product rule. So we get 2xy square, right, and then plus, then we are leaving the first factor unaffected, that is x square is left as it is. Okay, so we have x square, and then for y square we would go implicitly, so that will become 2yy prime. So that's the derivative of this part here, and then let's differentiate this portion here, or that term, and we know our derivatives respect addition, so we can just add them together. So here what will happen, first we differentiate this x cubed with respect to x, so we will get 3x square times y, okay, and then plus we will simply get what, x cubed, and then simply y prime. I'm copying and pasting for convenience here. So, and the derivative of 2 will of course be 0. So when we differentiate this equation, what we will get is, we simply get that this quantity here plus the quantity here, that sum is going to be 0, and then all that we have to do is we have to solve for y prime. So let me reduce the font size a little, okay, so here we go. So what we shall do is, we are solving for y prime, so we would go ahead and put the terms containing y prime together, and the other terms we will separate them, okay. So here we go. So we move that over to the right, and likewise we shall move this portion to the right, okay, and actually we could have moved it over to the other side. So what happens now is that we have collected the coefficient, the terms containing y prime together. Let me change this a little bit in like regular order. So in these two terms, if we factor y prime, what do we get? If we factor y prime, we get this. So y prime was a common factor, so this is the other factor, and then we got this portion on the without y prime. So what we will do is that we will move that over to the right, and it will change the sign in the process, and now all we have to do is that we will go ahead and just solve for y prime finally, okay, and that is what we shall have is negative, sorry about that, okay, negative, and then in the numerator we have this quantity here, right, okay, sorry, I'm having trouble copying it. So anyway, I can write it like this because this negative sign is outside and this goes to the bottom, okay. So that's the derivative of y with respect to x computed implicitly, right? And then so what we have is that if we want the derivative or the equation of the tangent line at 1, 1. So first let's just remove this, that's unnecessary. So for the tangent line at 1, 1, the slope is what? We shall just go ahead and substitute 1, 1 in the place of x and y here, okay. So if we substitute 1, 1, what do we get? We get a 3 here and a 2 here. I'm going slightly faster than before, and then for 1, 1 this would be, let me just, okay, that was a 2, and this will simply change to what? 1. So the slope at 1, 1 is what? Negative 5 over 3, Okay, and so equation of the tangent line would be what? That will be simply, I will just write that in the point slope form. So at 1 1 the tangent line has equation y minus 1 equals, okay, let me write that in the next line, negative 5 over 3, okay, so here we go, 5 over 3, and then here we have x minus 1. Okay, so let's input our line in here. We got y minus 1 equals negative 5 over 3, okay, x minus 1. And so in the GeoGebra graph you can see that we have gotten correct tangent line at 1 1. You can graph the tangent lines at 1 negative 2 and negative 1 2 in a similar fashion. Okay.